Negative 3 comes for the ride. Derivative of x squared is 2x. And then derivative of x cubed just became 3x squared. All right, is that going to have an answer? 26. Ah, no. What does this mean? We don't have real solutions here, do we? So what does that mean? This is a cubic function. If we look at this cubic function, do we know which side goes up and which side goes down? Yes. Left side goes down, right side goes up. Okay, so I know when I draw it, the left side goes down and the right side goes up, and I also know that I don't have any tangent lines that are flat, which means that it does not do this. It does like this. See? It never actually curves over. I can say that just by looking at this now. Now let's just say this had been negative 3 there. Then we would have two answers, and they would give us those 2 points right there. I want you to see the big picture here. All right, the big picture is that if we have a function, then we are now going to be able to find these humps, these peaks and valleys. We're going to be able to do it if we can set the derivative to 0, right? Let's get back to taking derivatives, though. And I also wanted to show you where that vertex formula came from. What happens, though, if this goes up to 4? Like, what happens when this power goes up to 4? What's the power on the derivative going to be? So if you take the derivative, what's the highest power in the derivative going to be? X cubed, right? And if I asked you to set that to 0, do you have a formula? Do you follow what I'm saying? Like if this was 3, we know that the derivative will always be a quadratic. And then we always have the quadratic formula. But if this is 4, and we take derivative, it's going to be a cubic function. And if we set that to 0, is there a formula? So everyone knows a quadratic formula, right? Do y'all think that there's one for cubic? It'd be nice, yeah? There is, yes, there is. There is, yes. What if this is 5th degree, and you take derivative, it'd be 4th degree? Do you think there's a formula for 4th degree? Yeah, there is. There is. And then what if this is 6th degree, and you take derivative of 6th degree, and you have 5th degree as a derivative? Set it equal to 0. You think there's a formula? There's not. So it's actually, and I'm going to have to double check this because I haven't actually thought about this in a while. The way I recall it is that there's a quadratic formula, there's a 3rd degree formula, there's a 4th degree formula. But once you get to 5th degree and on, there are no formulas. And it's not like we haven't found the formula. That's not what I'm saying. There's a difference between me saying we don't have one because we haven't found one, and me saying that it doesn't exist. And that's what I'm saying. It does not exist. So as soon as you get past 4, there is no general way to solve a degree, like a 5th degree polynomial set equal to 0. There's no general formula for it. It's been proven that you can't find it, that it doesn't exist. And I said I have to double check. What I have to double check is I don't remember if it starts at 5 or if it starts at 6. I just can't remember that, but I'm pretty sure it's at 5 and higher. You can't get it. All right, let's get back to some others here. Oh yeah, this is a nice one. I'm sorry, that's not that T. I didn't mean to do that. I'm going to let you just work with that for a second. I'm just going to go get a quick drink. I'm totally parched here. See what you think about that. Arturo. Where's Arturo? What do you see here, Arturo? So do you see like something plus something plus something where you could just go do each one individually? No, right? Okay, so what do you see? If you don't see that, then what do you see? Do you see a product or do you see a quotient? You see, where do you see a product? Quotient?
Yeah, X and sin X.
So this and this together?
No.
Oh, this over this?
Yeah.
Okay, good. That's what everyone needs to see. You ultimately have this thing right here divided by this thing right here. So we'll call that our F and we'll call that our G, even though we've already called this F. So you see a quotient, yes? Okay. So just go with it then. What's the quotient rule tell us the derivative of this should be?
Take the derivative of the sign.
Of this thing, of F, right? So we're going to take derivative of the top one first, right? Derivative of the top one, so I'm going to write it down. And then what? Times G, which is going to be x cubed minus 3x squared. Then what? Minus G prime, so the derivative of this. And then times F with no derivative, right? Am I done, Arturo? It's the quotient one. So there's one more thing we have to do. All of it over G squared. Okay, does everyone agree with that setup right there? Okay, now we'll move on to Ronnie. Where's Ronnie? Ronnie? You got to take those derivatives, right? Do you see how this problem's a little bit different than the ones we've done? What do you see, Ronnie, as being kind of different here? The x sine x, right? You have to take derivative of that. So how do you do derivative of this, Ronnie? What do you see here? A product, right? Which means you have to apply the product rule. Which means you might need to go do this on the side, okay? So you might have some scratch work over here now. Does everyone see that? We have a product rule that is occurring within our quotient rule. So over here on the side, my little scratch work, Ronnie's going to start cranking out the derivative of this, right? So now it's like we almost have a new little f and a new g, right? And we're just going to use the rule. So what is the derivative of this, Ronnie, according to the product rule? Should I write them up? Should I write them on the board so y'all can have them? Would that help? I'll put them up here just to remind you. If you have a product, it's going to be f prime g plus g prime f. If you have a quotient, it's going to be f prime g minus g prime f all over g squared. So those are the two things you should start burning in. So Ronnie, product f times g. So according to the formula, it's going to be, first is going to be what? Prime, so the prime of x times just sine x plus the prime of sine x times x, right? That's what Ronnie has to do. And so Ronnie, what's the derivative of x? One, okay, times sine x. So this is just sine x. And then derivative of sine x, cosine x, and then times x, right? I'm going to write it this way, plus x cosine x. So I decided to put the x out here in front. Now, Ronnie, this is just this, right? So all of this gets replaced with that. All right? See, it's a problem within a problem, right? And where we're headed is like problem within problem within problem within problem. Like a bunch of these things chained together. But it's very systematic the way we do this. So that is going to become that. I need it in parentheses. All right, and then Ronnie, you've suffered enough. You've gone through this to here, right? And I'm just going to continue to rewrite this. The x cubed minus 3x squared, and then minus, and now Daniela? Wait, no, Danielle. Danielle? It's you, right? Bateman? Yes. Is it Danielle or Daniela? Danielle. Okay, that last thing, I just keep on thinking that's an A on here. Just going to clean that up. Okay. Danielle. Danielle, where am I? I forgot. Done all this. Need that, right? So you okay with that derivative? Okay, what is it? 3x squared minus 3 times 2x, which would be 6x. Okay, and it's okay if we from now on go from here straight to here. And then we still have after that, right, x sine x. And we're not touching that. And then all of this over the denominator squared. And that, everyone, is the derivative. It's not pretty, but it's the derivative. Pardon?
Just stop there.
Well, we're done with the calculus. The calculus is over. At this point, anything we would do to this would be algebra. In terms of cleaning things up, we could, I mean, you would have to like FOIL this out, right? Like if you multiply these together, you'd have to FOIL it, and then you have to, like, well, FOIL here, that's only one term, so you just go here to here. This one you would have to go like here to here, here to here, here to here, here to here. But on your test, what I'm looking for when I give you these problems is this answer right here. And you'll hear me refer to this as the raw derivative. Raw meaning we haven't really done anything to it. We just applied the formula to it, right? The raw derivative. And the textbook doesn't talk anything about raw derivatives. I'm just telling you, when you hear me saying it, that's what I'm referring to. So on your exam, I'll want the raw derivative for sure. Now, keep in mind that later on, we're going to want to be trying to figure out where this thing has peaks and valleys. So we're going to want to set this equal to 0. So we're going to have to do algebra on this at some point. It's just not yet. Right now, we just make sure mechanically we can get to this, right? Then we do the algebra. Yes?
Will the homework answers be like that, or maybe just treat the whole thing?
When I do the homework on the videos, I usually just go to the raw derivative. But you bring up a good point. If you look at the answers in the back of the book, a lot of times they do weird stuff to the answers algebraically. And so your answer might be different than theirs. I wouldn't be discouraged by that. I would encourage you to try and make your answer look like their answer. I remember there's a story. I don't have a whole lot of time for this story, but when I was in graduate school, as a graduate student, we had to be teaching assistants. And so one of my duties was to, every Friday, there was a calculus class, Cal 1 like this. And every Friday that class had what's called a recitation, which is like y'all come to class, right? Like during the week y'all come to class, but on Fridays you go to a 1-hour question and answer session where you get to go ask questions. And the professor's not there. It's the TA, which is some graduate student, which was me. So I go in there with all these like 80 calculus students, because they had huge classes in these universities, right? So like 80 calculus students, I'd stand, walk up there and be like, any questions? And they could ask me pretty much any question out of the book, and it was tough, but you learned a lot that way. So I had this one student that didn't like me. He just didn't like me, and I think it was because, I don't know, I can't presume, but I mean, I was like I think I was like 20, and he was probably in his 30s. And he just didn't like learning from someone who was so much younger than him, I think, and he just didn't like me. So I was in the tutoring lab, okay, so I did my recitation or whatever, I got to an answer and stuff, and then we moved on, and then like later on, the next day, he went and found me in the tutoring lab, and I was helping a student, and he got all pissed off, like kicked the door in, like came in looking for me, and told me that one of my answers was incorrect. And told me that I need to go and, you know, apologize to the class and all this stuff. And so I was like, okay, well, maybe I made a mistake, you know, whatever. I looked at my answer, and I looked at the answer that he was looking at in the back of the book. And they weren't the same. But I could just look at it and see the algebra. It was like 12 steps to go from one to the other, you know? And I was like, okay, sit down. And I showed him, I said, this is algebra. And I just showed him all the algebra. And I said, you know, get out of here. Don't come to me with that. So my point is, I think it's a good challenge for you to take the raw derivative and try and make it look like the back of the book. Because you're going to get better with your algebra that way. It's tough, though. I mean, it's tough. But it's a good challenge for you to do it. All right? We just don't have time to take every single raw derivative here in class and take it all the way into its simplest form. I will when I can, but not all the time. Okay. All right, I have 20 minutes and we still have plenty to talk about. So I have got a really nice one for you. I have conveniently avoided this one. I would like to know what the derivative of tangent of x is. I mean, have I not avoided this one? I have avoided this one. We know the derivative of sine and cosine, that's fine. But this isn't sine or cosine, it's tangent. So let's see, we'll pull it, well, should we pull a stick? I don't know if you want to, do you have an idea? What do you got?
Oh, I looked at the first thing, it's secant squared x.
It's secant squared x. That's the answer. That is the answer. Good. Now, how do you get that answer? Okay, so you volunteered, so I'm gonna force you now. Okay, so look, all you have is the product rule and the quotient rule. That's all you have, right? And then a couple other rules. Tangent is not a product, is it? No, it's not tan times x. It's tangent of x. But can you look at tangent as being a quotient? Something over something?
Oh, sine over cosine.
Sine over cosine, right? So this is really sine x over cosine x. Okay, if that's sine x over cosine x, then can't you now use the quotient rule? Because you do know the derivatives of those, don't you? Okay, so let's do it. So if this is our f, and this is our g, and I'm sorry, what's your name? Jasmine? Okay, Jasmine. What is the formula? What are we going to be doing here? There you are. Derivative of sine x multiplied by g, which is cosine x, minus derivative of cosine x times sine x, all over cosine of x squared. Yes? Perfect. Everyone see that? Beautiful. This is great. And what's great about it is we know these derivatives, right? I proved that one to you using the limit definition, and this one I kind of proved. All right, so now you want to keep going? Because, all right.
So then it's going to be cosine of x
Times
times
cosine, times, no, this is cosine of x, right? Derivative, times cosine of x again, right?
X again.
So I'm going to say cosine x times cosine x, and then minus, okay, careful. Derivative of cosine x is not sine x, almost sine x. Negative sine x. Okay, so negative sine x times sine x again, right? All over.
Negative sine x squared. Or no, I'm sorry.
Yeah, okay, so you do not touch this one, right? That one just stays. All right, y'all good with that? Okay, what is cosine x times cosine x? Well, that's just cosine squared x. So that's cosine squared x. And then we have minus minus, right? Which is plus. And we have sine x times sine x, which is sine squared x. And then all of that is over cosine times cosine, which I have conveniently avoided just writing cosine squared x. Same thing, right?
Yeah.
And the numerator is 1. The numerator is 1. That's Pythagorean identity from pre-cal. But that is the same as writing 1 over cosine x, the whole thing squared, right? Because when you square 1 and you square cosine, you get the same thing. But 1 over cosine is secant. So this is the same as secant squared x, which is what you said it was, Jasmine. But now you know why, right? So you do not need to go through this every time. You know how everyone here already knows the derivative of sine x is cosine x? And derivative of cosine x is negative sine x? Now add to that, the derivative of tangent of x is secant squared x. Yesterday, in my Cal 2 class, I was doing a problem. I'm going to mute this because there's just a chance that this student watches. Yes? And guess what? There's 3 more. Pardon? I just unmuted it. Thank you, though. Yeah.
Wait, if that thing was like didn't have a square for secant, so would it just be negative tangent x?
Wait, what are you asking?
So with secant x, if there was no square, if it wasn't secant x or secant squared x, would the derivative still be like negative tangent x?
I'm not sure I understand what you're asking.
Well, because of cosine, the derivative of cosine x is negative sine x.
Uh-huh.
And if that was just secant x, and
You're saying if the derivative of tangent x was just secant x, is that what you're saying?
if it's negative, if secant x is the derivative of negative tangent x, like would it be the same thing? Because if cosine x is the derivative of negative sine x, which you did over there, would that also be that? I don't know if my question makes any sense. But
It's not making sense to me.
Tangent x the derivative of secant x?
Say it again.
Is a negative of tangent x secant x?
Is negative of tangent x the derivative of it?
Yeah.
yes.
Is that what you're saying? If you take negative tangent x,
Yes.
is that what you're saying?
Yeah.
And you take the derivative of this,
Would it be secant?
is that
Would it be secant x?
that would be negative secant x squared.
Okay.
Now, why would the derivative of that be negative secant x squared?
So then
Because this is a negative 1 attached to this with multiplication, right? So negative 1 is a constant in front of the function. Negative 1 comes for the ride when you take the derivative. Now you take derivative of tangent x, which we already know is secant squared x. So I think to answer your question is that the derivative of negative tangent of x is not secant x, it's negative secant squared
Okay,
x.
so then what would the derivative of secant x be? Would it just be?
Oh, okay, well, yeah, let's do that. So what would the derivative of secant x be? Right, that's what you're asking? Because we know derivative of sine, we know derivative of cosine, we know derivative of tangent. We don't know secant, we don't know cosecant, we don't know cotangent. And we should, right? Okay. So derivative of secant is on the table, and since you brought it up, and all you have is the product rule and quotient rule, Can you rewrite that as a product or a quotient?
Yeah.
Okay.
Be a little bit strange, but well.
What is the
how-
definition of
how we
secant?
Start out with that would probably just okay. So it's just that's just by itself, right? So I'm just using f times g.
No, because this is not f times g. This is secant of x. So there's no multiplication here.
All right.
So what did we do with tangent? We rewrote tangent as sine over cosine. Can you rewrite secant?
Oh yeah, you can rewrite it as 1 over sine x.
1 over cosine.
Sorry, yeah, sorry.
Okay, and now do you have like an f over g?
Yeah.
Okay, well, then we do the same thing now. Okay, this is our f. This is our g. What was your name again, sir?
Michael.
Michael. Okay, Michael. So according to the formula, you need to take, we're doing quotient rule, right? So we need to take derivative of f times g minus derivative of g times f all over g squared. So we're going to do derivative of what first?
That would be 1.
1. Derivative 1 first times g, which is the bottom, right?
Yeah, cosine x.
Okay, minus the derivative of g, which is derivative of cosine x,
Yeah.
times
Times
just 1 all over
all over 1, or sorry, cosine.
cosine squared x again, so I'm just going to put like that. Yeah? Now, Michael, what is the derivative of 1?
0.
0. So this whole term's gone, isn't it?
Yep.
This whole thing is gone because the derivative of 1 is 0. Over here, the derivative of cosine x is
That's negative.
negative sine x, but we have a negative out here still, right? Then times 1.
Yeah.
So it's just going to be sine x on top. And on the bottom,
It's,
cosine squared x. But Jasmine already knows that the formulas say that the derivative of secant x is? No? Did you have that one written down? No? So if you look at the formula, if you look in the book and on your formula sheets, it says that the derivative of secant x is secant x tangent x. Secant x tangent x. But that's exactly what we have here. Watch. This is, just tell me if you agree with this or not. This is sine x over cosine x times cosine x, which is the same as 1 over cosine x times sine x over cosine x. Just peeling it apart, right? And this, by definition, is what? Secant x. And this right here is tangent x. And that's the way you need to memorize it. The derivative of secant x is secant x tangent x. Now, do you feel like you could figure out the next two on your own? Okay. So the derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of secant x is secant x tangent x. The two we haven't done are cosecant x. Okay. Derivative of cosecant x is negative cosecant x cotangent x. And then derivative of cotangent x is negative cosecant squared x. They're on your formula sheets, but I would encourage that you just work through each one, okay? All right, I have 6 minutes. This next part you don't need to write down, but I also don't want you like packing up and putting your, never mind, just, okay. The product rule is a big deal, right? Quotient rule is equally as big deal, but I'm going to prove the product rule. Okay, I'm going to try and do it in 6 minutes. All right, so here we go. If I have two functions being multiplied, I'm writing it a little different. If I have two functions and I want to take their derivative, right? According to the definition, I need to take the limit as h goes to 0 of whatever my function is with x plus h plugged in minus whatever my function is with x plugged in. And then divide the whole thing by h. That's the limit definition. So if I plug x plus h into this, I get that, right? If I ask you to plug x plus h in for x. And then I subtract from that just the function itself without anything but x plugged in. And then divide the whole thing by h. All right. That is what we have to figure out, right? What is this limit? And somehow at the end, I need to show you that it's the derivative of the f function times the g function plus derivative of the g function times the f function, right? That's what I need to show it's equal to? Right? Would you be satisfied if I showed you it was this? Okay, now I'm going to work a little backwards from this because I think it'll help. This, by definition, is the limit as h goes to 0 of f of x plus h minus f of x all over h, right? Isn't that what that is right there? Yes? And then times g of x. And then plus, I'm running out of room, but this right here would be the limit as h goes to 0 of g of x plus h minus g of x over h. That's that, right? And then I'd have to have this times f of x next to it. Okay, that's just to give us a preview of where I'm headed, all right? So if I can somehow get this to show up, then I can turn that into that and I'll be done. So you can sit here and you can try a lot of different algebra on this. But in mathematics, we do something with things like this that's really kind of brilliant. You've been doing something like it for your whole life. Anytime you've had an expression like, let's say, square root of x plus 2 over x plus 1, and let's say we multiply by the conjugate, right? Everyone would be like, yeah, I can do the conjugate, right? The whole idea was that this right here is really what? That's really a 1, right? So multiplying by 1 never changes the problem, does it? You've been doing that your whole life, right? In little ways, like when you reduce fractions. This is a very useful but kind of basic thing we've been doing forever. To do this problem, we have to do something even more advanced than that. We have to realize that sitting right here is a 0. Okay? So watch. I'm going to rewrite f of x plus h, g of x plus h, plus 0 minus f of x, g of x. Now look, I would never, ever, ever, ever in a million years expect any of you to come up with this on your own. I'm showing it to you because it's worth seeing, all right? All right, so does everyone agree that there's a 0 sitting there? Yes? Okay, doesn't change the problem. So now what I'm going to do is I'm going to rewrite that 0, but I'm going to rewrite it in a very, very clever way. That 0, I'm going to make it plus f of x plus h times g of x minus, I'm going to run out of room. I'm going to have to rewrite it down here. Limit, h goes to 0. If I seem like I'm rushing, it's because I am. Okay, I'm going to add f of x plus h times g of x, and then subtract f of x plus h times g of x. And then I still have minus f of x, g of x, all over h. So does everyone agree that what's in blue is still 0? Yes? Okay. Now, I'll leave that there and do something really nice now. I'm going to take this one and that one and put those together, and then put this one and that one together. So watch what happens. Limit h goes to 0, f of x plus h, g of x plus h, minus f of x plus h, g of x. Yeah, I'll leave that. Plus, no, hold on. Yeah, plus f of x plus h, g of x, minus f of x, g of x, all over h. Okay, so like if we were to say that this piece right here is like 1, this piece right here is 2, this piece here is 3, and this piece here is 4, then I've just rearranged their order, right? This is now 1, this is 3, this is 2, and that's 4. Do y'all see all I've done is just switch the way they're arranged? Okay, now I'm going to do, because I only have 2 minutes, I'm going to do another shortcut. Break this into 2 fractions, same denominator. I can do that, right? Okay, now look at this right here. What do both numerators have in common? F of x plus h. I'm going to factor it out. I'm pulling it out. Okay, so that came out. So what's still there is this. Do y'all agree? Distribute, we're back to that. Plus, here, what do they both have in common? G of x. Okay, so what's still there? F of x plus h minus f of x all over h. Okay, we're there. Take the limit. What does that go to right there if you let h go to 0? What does that go to? That goes to f of x. Okay, times, if I take the limit of that, what is that? By definition, what is that? G prime. That's a derivative of g. By definition, right? Didn't you say that right here? That is that. Okay, so that's g prime of x plus g of x times, what's that when I let h go to 0? What's the definition? That's f prime of x. And that's what I was trying to show you, right? Okay, I got it all in. So that 0 is weird, right? Like, where would you ever come up with that? Homework. Homework. You should finish everything in 2-3. Okay, that's basic differentiation formulas. Make sure you do all of 2-3. And then as far as 2-4, get as far as you can. I mean, we've covered the rules, so see how far you can go in that section for homework. All right, have a good weekend.